Jiuzhang manipulated hundreds of photon modes simultaneously, and the research team's published claim is that their hardest regime result would take the world's fastest classical supercomputer longer than the age of the universe to replicate. That is the kind of number that stops a conversation cold. It is also exactly the kind of number that demands a harder question. Before you file this under state-sponsored lab theater, consider one thing. The photonic architecture behind Jiuzhang is the same fundamental approach that PsiQuantum, a Western company with over $700 million in publicly reported private funding, is betting its entire existence on. This is not a fringe program chasing an exotic detour. The photonic route is where serious capital on both sides of the world is pointed. So the real question is not whether Jiuzhang broke computing. It is whether a strong photonic platform puts China credibly close enough to crack even one narrow, real problem first, and whether that narrow first win is the thing that actually matters. By the time you reach the end of this, you will understand what quantum advantage actually means, and more importantly, what it does not mean. You will know why the photonic route is the specific battleground, and you will understand the two bets at the center of this race. Because they are not the same bet, and only one of them can be right. This is not a story about a processor setting a speed record. It is about who gets close enough to the ceiling first on even one problem that actually matters, and whether arriving there first lets you write the rules everyone else inherits. Now, why photons at all? Because to understand what Jiuzhang did, you have to understand the engineering problem it sidesteps, and the different engineering problem it runs straight into. The dominant approach to quantum computing right now, the one Google and IBM have built their programs around, uses superconducting qubits. Those systems have to operate at roughly 15 millikelvin C, about 15 thousandths of a degree above absolute zero. To put that in physical terms, the open space between galaxies sits at around 2.7 Kelvin. A superconducting quantum processor runs colder than that. You're engineering and maintaining an environment more frigid than the cosmic void, inside a building, at scale, without disrupting the quantum states you're trying to control. That is an extraordinary feat of engineering, and it is also an extraordinary constraint. Photons do not require that. A photon carries a quantum state naturally at room temperature. It is what light does. Photonic quantum computing lets you sidestep the millikelvin freezer problem entirely. Think of superconducting qubits as an engine that only runs inside a chamber colder than the surface of Pluto. Photonic qubits are the engine that can run in your living room. The catch, and there is a real catch, is that this engine only runs one very specific type of race. Photon loss is hard to control at scale. Reliable 2-qubit gates, the building blocks of programmable computation, are difficult to construct with photons in ways they are not with superconducting systems. And no photonic system anywhere has demonstrated fault-tolerant, logical qubit computation, which is what you would need to run a general-purpose quantum algorithm with confidence in the output. So what exactly is Jiuzhang doing? Jiuzhang performs a task called Gaussian boson sampling. It is a mathematical procedure that involves preparing photonic quantum states and measuring the output distribution, a task that maps naturally onto what photonic hardware does well. The key thing to understand about Gaussian boson sampling is that it was not a workload anyone was running before quantum computers existed. It is not an optimization problem someone was stuck on. It is not a calculation holding up a drug discovery pipeline. It is a task that is hard for classical machines and natural for photonic hardware, which makes it a meaningful engineering test, but not a neutral one. The gap between sampling faster than a classical machine on this specific distribution and actually accelerating a real computation is enormous. It is like breaking the world record for the 100-meter dash on a track built specifically to your stride length, with a tailwind, in a category no one else entered. You ran fast. Whether you can win a race that anyone else cares about is a completely separate question. Does this mean Jiuzhang's result is meaningless? No. Demonstrating control over large photonic systems at all is a genuine engineering milestone. The Jiuzhang 2 results were published in peer-reviewed journals. Jiuzhang's program has shown photonic manipulation at a scale that demands attention. The question is whether that engineering capability translates to a problem anyone needs solved, and that is exactly what the two bets disagree on. Which brings us back to PsiQuantum, because PsiQuantum is making a related architectural bet and has far more capital. So why is it not further ahead? Because PsiQuantum and Jiuzhang are not actually running the same race. PsiQuantum's stated approach, according to the company's own public roadmap, is fault-tolerant photonic quantum computing. Full error correction, logical qubits, general-purpose quantum computation done right. PsiQuantum has not published results from a working quantum processor. That is not a claim that PsiQuantum has failed. It is an accurate description of where the public record stands. The company is building what it describes as the interstate highway system before putting a single car on the road. It believes that specialized demonstrations, the Jiuzhang track, are ultimately a distraction from the harder problem that actually needs solving. Jiuzhang's program is doing the opposite. It is pursuing near-term specialized advantage on the sampling track, demonstrating photonic manipulation at scale without error correction on a purpose-built task. It put a car on a dirt track and drove it very fast. Neither program has proven it can move cargo cross-country. On the specialized sampling track, Jiuzhang has demonstrated more than PsiQuantum has published. On the fault-tolerant track, neither is close. Whether the specialized track matters at all is exactly the disagreement the two bets encode. But before you back either one, you need to look at what the classical simulation counter-arguments actually say about Jiuzhang's headline claim, because that age of the universe number has a complicated history. The pattern here is established and important. When Google published its 2019 Sycamore quantum supremacy result, claiming a task that would take a classical supercomputer 10,000 years, IBM responded within days with a classical simulation argument suggesting the task could be done far faster using a different classical approach. The quantum team moved to harder regimes. The classical simulation researchers kept working. The cycle continued. The same class of counter-argument applies to Boson sampling. Classical simulation researchers have published algorithms that reduce the estimated computational cost of simulating boson sampling tasks generally. The age of the universe framing in Jiuzhang's team claims applies to the hardest theoretical regime, not necessarily to the specific circuits the experiment actually ran. The exact classical hardness of Jiuzhang's specific photon configurations remains actively debated. No independent third-party verification has settled this question in the way you would want, before treating the claim as closed. What does this mean? It means the photonic engineering is real. The classical intractability claim is the part that carries genuine uncertainty. Those are separate things, and conflating them is how both the hype and the blanket dismissal get this wrong. Jiuzhang is not fake. Its headline hardness claim is contested, as every frontier quantum claim has been from every team in every country. So with that honest read on the evidence, what do the two bets actually mean for the compute ceiling? The ceiling that artificial intelligence researchers actually hit today is specific: training very large models, running certain optimization passes, simulating molecular systems for drug discovery or materials design. Of these real workloads, molecular simulation is the most credibly mapped to quantum hardware. It is a problem where quantum mechanics is the subject of the computation, not just the tool. The research community broadly regards quantum chemistry as the most plausible near-term application where quantum hardware might genuinely outperform classical machines. Sampling-style problems, the kind Jiuzhang excels at, have some conceptual overlap with generative modeling and machine learning. But the bridge from one to the other is not established. Quantum speedup on any artificial intelligence training or inference workload remains an aspiration, not a demonstrated result. The pattern that matters here is the graphics processing unit parallel. Graphics processing units were designed to render polygons. Nobody called them artificial intelligence accelerators. Then one narrow workload, matrix multiplication for neural networks, turned out to map almost perfectly onto what those chips already did. The industry reorganized around them inside a decade. The question for quantum is whether there is a matrix multiplication moment waiting inside sampling or optimization. A narrow problem that nobody quite recognized as quantum native until someone ran it and the numbers came back ridiculous. Why does it matter which country finds that moment first? Because the narrow win defines the application template. It attracts the talent. It shapes which hardware architecture gets funded for the next decade. The country that demonstrates a real result, even on one specific problem, gets to set the early rules. That is the ceiling that actually matters right now, not the general promise of fault-tolerant quantum decades out. Here's my honest read. The triumphalist version of this story, that China has already cracked the artificial intelligence compute ceiling with Jiuzhang, collapses under its own weight. The task is purpose-built for the hardware. The classical hardness is contested. No useful application has been demonstrated. Anyone telling you the ceiling already moved is ahead of the evidence. The dismissive version, that Jiuzhang is pure optics with no engineering substance, is equally wrong. Manipulating photons at this scale is a genuine achievement. The photonic route is the same one Western capital is backing at meaningful scale. Treating the result as propaganda requires you to also dismiss PsiQuantum's architectural premise, which the people who wrote the checks have not done. My read is this: the ceiling has not moved yet. But Jiuzhang's program means China is standing close enough that if a narrow, real-world problem turns out to map onto photonic hardware, the way neural networks mapped onto graphics processing units, China is in a credible position to crack it first. That is not a win. It is a viable position in an early race. And in a race this early, a viable position is what determines who sets the template everyone else builds on. Here's what I actually want your read on. Actually, Bet A says a specialized photonic machine will crack one real compute-heavy problem before fault-tolerant quantum arrives. And that first crack is what reshapes the field. Bet B says the gap between a sampling record and anything useful is so large that no specialized machine bridges it, and this whole era of demonstrations turns out to be a detour. Which bet would you back, and what would have to be true for the other one to be right? Tell me in the comments. I want your honest read. If you want to follow which bet the evidence actually starts to confirm, when a photonic result lands on a problem that was already on someone's real workload. Subscribe, because that is exactly the moment this channel will cover when it happens. The ceiling is still there. The question is, who is standing close enough when it finally cracks?